So hello sir, today I'm going to present this paper of speech-to-face, learning the face behind the voice. So let's get started. So let's understand the motivation of this paper. So basically, whenever we hear someone's voice, we can easily infer their age, their gender, their ethnicity from their voice, and then we can somehow able to reconstruct their face using their voice in our brain. So basically, we can then imply that our voice contains some of the facial features that we might don't know. So for example, if I play this,
There'll be someone after me, and so hopefully someone after them again. So it's there'll be someone after me.
so we can directly infer that the person speaking here is a male and the age is something around 40 to 50, and he's from Britain because of its British accent. And next,
Me, whether it's in a French film or whether it's in a Bhojpuri film or it's in a Hollywood. It's me, whether
so again, listening to this voice, I can infer that the person speaking here is female. She's from India, and because of her accent, and she's around 40 to 50 of years of age group. So we can infer that from the voice, we can infer many of the features, including the facial features we may not know. Since we're able to reconstruct the face listening to the person's voice. So this is the main motivation behind this paper. So let's understand some of the historical perspective on the multimodal learning in this domain of self-supervised learning. So before before in the audio visual corresponding task, we don't have any automated way of seeing the correlation. We have done mostly the manual work, like the matching the speed with the leap movement and all. But after 2016 and 2017, Anand Voik and Jesselman, they introduced the audio visual corresponding task using self-supervised learning. That means they have the video, so they have the audio and the image, the corresponding image. So because they have the audio, and they are somehow able to naturally correlate the audio and the video without any human intervention through self-supervised learning. So this is a breakthrough in our context, and this also results to some recent developments like the sound source localization, some separation, some cross-modal retrieval, for example, searching for the images based on audio queries and vice versa, and then on audio visual representation learning, that is creating joint embedding of the audio and the video, of the audio and image, so that they can explain both of them simultaneously. So now let's now deep dive into our speech to face model, the technical aspect of the model in detail. So the model architecture is quite intuitive, that we can say. So we are following the concept for the concept of the self-supervised learning here. That means we don't have any explicit labeling of our data. Instead, we have only the images and the corresponding audio, and from that to model from the data of different modalities, we have to learn something using our model. So the data set used here is the ABC data set, which contains around millions of YouTube videos, clips with speaking faces. That means basically I would say we have the speech and the corresponding face of the person speaking there. So over over a lakh of different speakers we can see, and some diverse demographic representation also observed, like ranging from English group, Asian, and so on. So this is the dataset statistics in terms of the age, ethnicity, and the mere gender. From the histogram of age, we can directly infer that the age group is more biased towards the age group between 22 to 30, and the ethnicity is more biased towards the white people, and we can also see that the gender is more biased towards the male population. So this is our data set. So this is our complete model pipeline. So let's understand this model in detail. So basically, and this model is quite intuitive. So here we are first encoding the so again we have to use the concept of self-supervised learning so that we can train this model. So we have the image and the corresponding audio. Since we have the video, we can extract the image and the corresponding audio signal. So we have a face encoder, a pre-trained face encoder, and this pre-trained face encoder will not be trained again during the training process of will not be used in the training process of this speech encoder model. So the main role of this face encoder model is to take in the image and encode the image in some low dimensional representation of 4096 dimensional face features. And this phase decoder will take this 4096 phase features, dimensional phase features, and try to reconstruct back the original image. So this is the main idea of the phase encoder decoder model. And in this model architecture, we will use a pre-trained fixed phase encoder decoder model, which will not be trained further in the training of the speech encoder model. So in the speech encoder model, we will take in the waveform that we had, that a speech we have, we'll pass it through the speech encoder model. We will understand this encoder model in detail in the further section, and it will also encode the speech signal to the same dimensional representation, that is 4096 cross 1 dimensional representation, and then we will calculate the loss. So again, our main idea is to align this voice encoded feature and the image encoded feature as much as possible. So we will somehow calculate the loss between these two feature function, and after calculating the loss between these two feature, we will back propagate only through this speech encoder model and update the weights, and we can do it for multiple epochs so that we can get a perfectly working model. So this is the main model architecture. So now let's understand the voice encoder model in detail. So the voice encoder model will take in the the audio wave file, pass it through the complex spectrogram, and after that we will apply CNN, and then we will get a 4096 dimensional phase features. So let's understand this spectrogram in detail. So the complex spectrogram will give us the 598 cross 257 dimensional representation of the 6-second audio clip, and it is in two channels. That means one is for imaginary, one is for real. So hence in the CNN blocks, we will give an input of 598 cross 257 cross 2, and the CNN blocks is contain approximately 8 to 9 convolutional layers, followed by the batch normalization and radio activation function, followed by some fully connected layers, and then we will get a 4096 phase dimensional features. So this is the complete architecture of the CNN blocks that will take 598 cross 257 cross 2 as input histogram, and then we have a series of convolutional layers followed by pooling layers and some fully connected layers, so that it can give a encoded representation of the speech signal in the 4096 cross 1 dimensional representation. So basically we are applying STFT to convert those speech signals in the corresponding spectrogram, and this spectrogram will be taken into this complete CNN block to get the final 4096 phase feature vector. So in the phase decoder model, we are using the model by Coley et al. So the main role of this phase decoder model is to reconstruct, it tries to reconstruct the frontal orientation, the natural expression and the normalized lighting condition from the low dimensional representation, which is 4096 cross 1. So here it will take the feature vector, in the first layer transform it to a 1000 dimensional representation, and this particular decoder model is not trained during training process of the voice encoder model. So this voice encoder model weights will get updated after each epoch, but the phase decoder model weights will not be updated after each epoch. So let's again start from the first and understand the complete pipeline of this model. So we have the ABC speech video clip, we know it very well. Yeah, we will segment this video clip into a clip of 6-second videos. Then we are getting audio clip from there. There is 6 seconds from the start of the clip and repeat if less than 6 seconds. And then we will resample the audio of at 16 kilohertz, and only single channel is used there. And then we will apply a spectrogram. Okay, we have seen that spectrogram after applying the STFT we are getting 598 cross 257 cross 2 dimensional spectrogram. Why? Because we are using a hand window of 25 millisecond, that is each audio length in that for which I am finding the spectrogram is for 25 millisecond. The hoop length is 10 millisecond, and hence we are getting approximately 600 time beats, because we have 6-second audio clip divided by 10 millisecond, which is approximately 600 time beats, and 512 F50 frequency beats. And after that the S goes through the power law compression, resulting for the real and imaginary independently. So why this? This is something needed because of the perceptual quality, and hence we are applying the power law compression by signum of s to the power 0.3. So in the face encoder model, we are using a simple CNN based delip face detector to crop the face image. First we will try to crop the image using the delip face detector, and we will pass that cropped image through the VGGNet encoder model, which will give us this 4096 face feature vector. So this is the complete pipeline. So now till now we are able to get this low dimensional representation, and then this face decoder will take in this particular speech encoded feature vector and tries to reconstruct this face image similar to that of the input image. So let's understand the loss function. So now we are here, that means we got the face encoded feature vector and the speech encoded feature vector. So we will try to minimize the loss between these two encoded feature vector. So the very naive loss function that we can think of is the L2 loss between the two feature vector, and using that L2 loss we can somehow backpropagate on the speech encoder model and we can update the weights. So this paper also did the same initially, but they have found it's taking too much epoch, too much time to train a very good model. So they have updated the loss function, and there are three terms in the loss function. The first term here, there is f decoder VF here. So this VF and this VS is the feature vector. So this is VF. VF is the 4096 face encoded feature. VF is the 4096 dimensional speech encoded feature. And then we have the F decoder and F decoder. That means we have seen that in the face decoder model, we have a first layer which transform the 4096 dimensional representation to 1000 dimensional representation. So this F decoder is the same. That means after passing each of the feature vector through the first layer of the VGGNet, we are getting 1000 dimensional vector. So this FDEC is that particular 1000 dimensional vector. So we are finding an L1 loss between these two transformed feature representation. And the second term is trying to align the direction of the face encoded feature and the speech encoded feature. That means the face encoded feature and the speech encoded feature lies in the same direction. And the third term is calculating some sort of knowledge distillation loss. So FVGG and FVGG represent the feature vector that we are getting after passing the encoded feature, that means facial feature and the speech feature through the VGGNet, and then we will apply the knowledge distillation. So the main, so this is the formula for the knowledge distillation. Somehow we can expect here. So basically, what is the main intuition behind this knowledge distillation? So it ensures the behavioral similarity using the pre-trained VGGNet face features. So this is the main intuition behind this knowledge distillation loss. So the total loss is a combination of three loss functions that we have inferred very well. And these are some of the hyperparameters and the optimizers used. So the optimizer uses Adam optimizer and some of the hyperparameters as mentioned here. So now let's understand the result of our model. So let's listen to this.
Hopefully someone after them again. So it's
So again, from this voice we can infer that the person is from Britain. He is a male, yeah, and he is a male, and somehow the age is something between 40 to 50. So we can see that the face, that this is the reconstructed face from the speech using the model, and this is a true face. So this reconstructed face is somehow able to capture the facial features, some of the facial features, some of the chemical features, and also it's able to capture the age, the ethnicity, and the gender of a particular person. So we can see the model is performing quite well. And next,
whether it's in
so next we can see the person here speaking is somehow Indian. We can infer from her accent. She is a female, and her I would say ethnicity is Indian, and age group is something between 40 to 50. We can infer from the voice. So again we can see that the model is somehow able to capture some of the facial features, or I would say the gender and the ethnicity and the age group. So this is the results of the model. So initially we can infer that the model is performing very well. let's dig back into the result analysis. So first, we can see that in the qualitative results, we can see that the model is very well able to capture the ethnicity, the age, and the some of the facial features of the person. So we can it's very evident from this we can this column represent the reconstructed face from the face encoded features, and this is the reconstructed face from the speech encoded features, and we can see they are quite similar. So the model is performing very well. So now let's analyze the demographic attribute analysis. That means how well the model is performing across the age group, across the ethnicity, and across the gender. So before that, let's again revise the dataset distribution. So the age group is more biased towards the 20 to 30 age group. The ethnicity is more biased towards white people, and the gender is more biased towards the male population as given here. So we can see in the gender classification, 95% overall agreement between the accuracy is found, and 84% of accuracy are found in males and 84% in females. We can also see in age estimation that we can also see a strong diagonal pattern in the confusion matrix, which implies that across each of the group, the model is performing very well, or the accuracy is very high across each of the age group. And also we can see that the best performance is for younger and middle age adults. Why? Because our data set is more biased towards its 20 to 30 age group of the people. In the ethnicity, we can see the highest accuracy is for the white people, followed by Asian, Black, and Indian. Again, the reason is quite straightforward, that the data set is more biased towards the white people as compared to that of the other ethnicity. So now let's understand about the craniofacial measurements. That means, what is craniofacial measurement? It's basically giving us how well the model is able to capture the facial feature of the person. So the facial feature or the facial measurement includes the upper lip height, jaw weight, nose height, nose width, etc. So we can see the correlation is something ranging from 0.11 to 0.35, and the p-value is, again, for all of the cases, it's something less than 0.001. Again, they are very well performing from the random baseline. So interesting result. So what is the main interesting result here? That is, the strongest correlation we have found here is for the nose related feature. Why? Because our voice and our nose activity is highly correlated. If my voice is changing, somehow my nasal activity is also changing very much. So we can also infer that the speech and the nose related features, for example, nose height or nose width, they are highly correlated, and hence we can see a strong correlation appeared in the nose related features. So now let's understand about the cross model retrieval performance. So before that, let's understand how the video duration changes the performance of the model. So we can see across each of the metrics, if I am increasing the video duration, the performance is increasing. It's quite straightforward, because a longer duration video will capture more information about the correlation between the audio and the images. So hence it is very evident that the longer duration video sample will perform well as compared to that of the 3-second one, and it's quite evident from the results we can see here. So next, now the researcher is trying to retrieve the correct face from the database of 5,000 images. So this terminology of R@K represent the top K selection, like how likely the true image lies in the top K selection of the reconstructed face from the database. That is, if I have a reconstructed face, I have 5,000 images, and from that reconstructed face, I'm finding out the top K most similar images, and how likely the true image lies in that top K selection in percentage. So we can see R@1, that means that the top selection is the true image, the accuracy percentage is 5.86, and so on. So here also we can see that if I'm increasing the duration, the performance in the top K selection is increasing across every metric. We can, and across every K values from ranging from 1, 2, and 5, and 10. So what is the conclusion? So we can see that the voice carries some meaningful information about the facial appearance. Yeah, it can capture easily the age, it can capture easily the gender, the ethnicity, and the facial structure, some of the facial structure. and this is something a breakthrough, because now we can see that our voice captures some of the facial information which we can reconstruct from our brain cells. That's the idea. So our brain reveal about more about our physical appearance than we might expect. Okay, our voices reveal more about our physical appearance. Okay, so that is the most interesting part. So again, what is the reflections that I'm getting? That the most exciting results. First is the craniofacial correlation. That means our facial features in our voices are highly correlated, especially the nasal activity, which is quite evident. Next, and also we have also seen some demographic bias effects. Again, it's only due to the unbalanced data set that we can use. So in the scope of improvement, we can further analyze the data set and make a comprehensive, well balanced data set across each of the age group, across each of the ethnicity, and across the gender. We can also uh, add some more modalities. That is, we can also incorporate some linguistic content analysis alongside acoustic features. Might improve the reconstruction because of the consideration of the linguistic side, as certain speech patterns correlated with culture and the regional facial characteristics. We can also next we can also focus on the dynamic face reconstruction. Till now, we are only focusing on the static face reconstruction, but now we can also focus on some neutral faces to reconstruct the plausible facial movements during speech. Will be fascinating extension. So this is about the paper of Speech2Face, that is learning the face behind the voice, that way how the voice can be used to reconstruct the face of image. And yeah, thank you so much.